Welcome to the next lecture on multivariable calculus. In this lecture, we will consider functions of several variables. We will talk about their limit and continuity. As in the theory of functions of a single variable, the concepts of limit and continuity figure prominently when we consider functions of several variables. So let me begin with continuity roughly. The statement that the function, say f, is continuous at a point q should mean roughly that for all points p near q, the value of f differs, fp differs but very little from the value of fq. Let me write it here and with definition I'll show you. So as I said, that function f is continuous at a point means whenever we have a point p near q, the value of fp is it should be a value of f should be near fq. Let us see a precise definition. So here we have a set A in Rm and we have a function f from A taking values in Rn, means it is a vector valued function. Suppose we have a point q in A, then we say f is continuous at the point q if for any epsilon positive we get delta such that this thing happens. This means whenever p is near q, fp is near fq. Okay. So in this case, what we are doing, we are in this side, we are taking norm in Rn, and this shows norm in Rm. As you can observe that this definition is very similar to the definition for definition of continuous functions of single variable and taking values in R. Okay, this is almost same definition, only the difference is here instead of modulus we are using norm here. Okay, and you know both norm and modulus gives us the distance or the metric. Okay, so here we have defined continuity at a point. What about continuity of a function in a set? Okay, for that we can say if a function f is continuous at every point, function is continuous at every point of a set A, then we say f is continuous. Then we say f is continuous in the set A. Correct? And we know this notion of continuity, this is closely related with the notion of limit. Okay, notion of limit and continuity, they are closely related, and continuity are closely related. Let us see how. Let us see how. Now suppose f is a function from a set in say Rm to Rn. So here domain of f is the set A, which is a subset of Rm, and suppose q is a point in the closure of A. Q is a point in the closure of A. We say We say f has the limit L, has the limit L for P tending to Q. If for every epsilon positive, we can find a delta which is again positive, such that norm Fp minus L is less than epsilon whenever P is in A, and in fact P lies in a deleted neighborhood of Q. Okay, again here this norm in this side is norm in Rn, and norm here is norm in Rm. Okay, if we have this thing, if a function satisfy this, we say in this case we write in this case we write limit Fp p goes to Q equal to L. Okay. Now see here, let us compare both the definitions. In the definition of continuity, we took Q a point in A. However, here in this case, we took this point Q in the closure of A. You know, closure of A is the set of all closure points, meaning a closure is A union its set of its limit points. Okay. So this means we cannot directly say that if a point Q lies in A closure, then it will lie in A. This is not the case. But what happens if this point Q lie in A? Okay, in case Q lie in A, we can have we can take these P as Q, and they lie in A, and you know this condition in that case means norm P minus Q is always less than delta for any delta. Okay. So what we have is norm P minus Q is less than delta for any delta. Therefore we have Fp minus Fq less than so here what we have is we have Fp minus L less than epsilon, and you know we are taking P equal to Q, so we can write Fq minus L less than epsilon, and this is true for all epsilon positive. Okay, what we get from here, this implies Fq is nothing but L. So what do we get? We get limit Fp as P goes to Q is nothing but Fq. It was L is now Fq. So therefore we can write a function f is continuous at a point Q, f is continuous at a point Q if we have this condition. Okay. So this means these two are equivalent statements. Now Now what we assume now is, here we took the case when Q is in A, means F is defined at this point, okay, because the domain of F is A. Domain of F is A, and we are saying Q is in A. This means F is defined at the point Q. And in this definition, we are taking Q coming from the closure of A. What happens if F is not defined at the point Q? Okay, if Q coming from A bar and F is not defined at the point Q, at Q. So this means F is not Q is not a part of A. And suppose F has a limit L for P tending to Q. So in this case, we say that this F. So in this case, what can we do? We can extend this function F naturally and define another function which will be continuous at the point Q. So then we can naturally extend the definition of F to the point Q by defining Fq equal to L. Okay. The function F extended this way will then be continuous at Q. So this means if F is continuous in its domain, we can extend the definition of F as limit not just to a single boundary point Q, but simultaneously to all boundary points of A, for which F has a limit. The resulting extended function is then again continuous. So we will see this by an example. So whatever I said, let me write that. So if F is continuous in a set or in its domain, so in the above case, here we extend this F to the point Q. Now we can extend this F to all boundary points of A. We can extend the definition of F as limit to all boundary points of A, for which F has a limit. And the extended function will be will be continuous. Okay, now let us see an example. Let's see an example in case of R2 function from R2 to R. Okay, let we take A equal to A is defined by this, the upper half plane in R2, and define a function f from a to r given by fxy equal to e minus x squared by y. Okay, then one can easily check this f is continuous at all points of a. It is easy to see that f is continuous at all points of a, means f is continuous in the upper half plane. Now, so what is upper half plane? So here we have xy plane r2, and what we are doing, let me write. So suppose this is our x-axis, this whole part is upper half plane, the domain, this is a, okay, the domain of f. Now consider a boundary point. Boundary point will be somewhere here. Boundary point is here, okay, in the in the x-axis. Consider a boundary point zeta comma 0. Whenever zeta is non-zero, okay, so whenever zeta is non-zero, consider a boundary point zeta 0. For zeta non-zero, we have limit xy going to zeta comma 0 fxy. What is this? Fxy is e minus x squared by y. So this would be e minus x squared by y, xy going to zeta comma 0. So it will go to 0. Okay, and this go to 0 when this y coming from this side, when y coming from 0, y is positive coming from upper half plane and tending to 0. Correct? What about what about the origin? Okay. Uh, so 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 here what we have taken that outside the origin. So this point is the origin, the 0 comma 0. Outside this origin, on the boundary of the upper half plane, we have limit of this function at 0. So we can define another function. We can, so thus we can extend. Thus we can extend f. Uh, extend f means we can define another function f star. Okay, f star, which will be same as f when xy coming from a. This means if y is positive and x in r. So this was a, and this will be 0 if y is 0 and x non-zero. Correct? So we can define another function f star, meaning we can extend f. Okay, here you see, when we restrict f star to a, we will get f. This is the definition of extended function. So what we get, this new function will again be continuous, and this is continuous. So here we know f star is continuous on say upper half plane. closed upper half plane minus the origin. So what about the point origin? What about the point 0, 0? So can we extend f to origin as well? So let us see. At the origin, now let me draw a figure. So here we are in R2 and we are saying in closed upper half plane minus the point 0, 0 means this point. Okay, this point, we are removing this point. So in this set, f can be extended and we call it f star. Now let me take a set in this upper half plane, closed upper half plane. Take this set y equal to, say, this set y equal to x. Okay, whenever y equal to x, take this set. Let me draw it. Uh, so what happened when y equal to x? So when y equal to x, f star x comma y would be e minus x square by x, y equal to x. Okay, so this is e minus x. Can I say something? No, I can't. So I have to take another curve. So which curve? Okay, it is of this form, x square by y. So let me take another curve. Now consider curve y equal to x square, the parabola. Okay, so here let me draw it. So suppose we have y equal to x square and we come to, so these points are tending to the origin along this curve y equal to x square, along the y square. Then what will happen? Let me see. Okay, when y equal to x square, fxy is e e e, e minus 1. Okay, so it is e minus 1. And when y equal to, say, 2x square, fxy is e minus 1 by 2. Correct? So for two different curves, we are getting different values of f. And when these points going to going to 0 or the origin along these curves, we will get different values. Okay, in case of this curve, the limiting value would be e minus 1. In case of this curve, the limiting value will be e minus half. Okay, we are getting different different values of limits. So this means along different parabolas, or okay, parabolas tending to the origin, f has different limits. Okay, we are not getting a single limit. So this means f is not continuous. Therefore, f is not. Okay. Therefore, we can only say f is so. Let me say like this. Therefore, uh, uh, fxy. Uh, so what can I say? Therefore, as xy goes to 0, f does not have any limit. Okay, so does not have any single limit. So you see, you have does not have any single limit or well-defined limit. Thus, we cannot extend this function to the origin. This example shows that a function of several variables may have discontinuities of much more complicated type. Okay, it has discontinuities of much more complicated type than a function of single variable. To say this, let us see some more example. So what kind of discontinuities we may have? So here is another example. We can have discontinuities along a whole arc of curve, not just isolated point. Discontinuities may occur along whole arc of curve, not just a, not just a single point or at isolated points. To see this, let us consider the following example. Consider this function, which is defined like this. For x not equal to 0, this is y by x, and when x equal to 0, it is 0. So you can easily see that this function is discontinuous along the line x equal to 0. This function is discontinuous along the entire line x equal to 0. Okay, so here you see so let me write this. So this was R2, and uh, so this whole line was, so at each point of this line f was not continuous. Now there are functions of several variables which are continuous in in the variable x when we fixed y, and these functions are continuous in y for fixed x. Okay, but they are not not continuous function as a whole. So let me write it. There exist functions of several variables which are continuous in x for each, okay, for each fixed value of y, and similarly continuous in y for each fixed value of x. Yet the function as a whole, it is discontinuous. Yet be discontinuous as a function of x comma y. Here is an example in the support of this. So we have an example. Now take function f, which is defined like this when x y is so outside the origin, this is this function, and in the origin it is in the origin it is 0. So you know, for any fixed y, so what we will show, for any fixed value of y, function is continuous in x, and for any fixed value of x, function is continuous in y. So let us see this. For a fixed y non-zero, and let me take y equal to some k. So what is fxk? This is 2xk divided by x square plus k square. K is non-zero. Okay. Since k is non-zero, this part is always positive. K square is always positive. You see, the numerator is always positive. Numerator is always positive. It's never zero in this case. For any value of x, it's non-zero. Therefore, this function is continuous. So f is continuous as x square plus k square is always greater than 0 for k non-zero. What about for y equal to 0? For y equal to 0, fx comma 0 is it's 0. Okay, which is, you see, for x in R, for any x in R, this is a constant function. So for y equal to 0, fx 0 is 0, which is also continuous. Which is also continuous. Similarly, we can see that f is continuous in y for each fixed value of x. But what about as a whole, as a function of xy? So, there is a term that separately continuous. So these functions are separately continuous in x and y. But what about as a function of xy, whether this function is continuous or not? For that, let us consider some curve. Okay, here we take this curve y equal to x. Now consider its value in this. So consider its value in, so fxy when y equal to x, fxy is 2x square upon 2x square is 1. So fxy is constant. Okay, fxy equal to 1. Now let me write fx comma x equal to 1. So whenever these points tend to the origin, the value of fxy is always 1. Fxy is always 1. But what about f00? We have defined here f00 is 0. 00 is 0. So the limits, what happened? What is this? So here we have f00 is 0, but the limit x goes to 0, fx comma x, this is 1, which is not equal to f00. Means this function is not continuous. This function is not continuous at the origin. So therefore, f is not continuous at the origin as a function of xy. However, it was continuous separately, means it was continuous when we fixed value. So for a fixed value of y, f was a function of x and it was continuous. For fixed value of x, f was function of y and it was continuous. But as a function of xy, this function is not continuous at the origin. Let us see how does this function look like. (3D calculator). Let me go here. 3D graphs, 3D calculator. Okay. So this is 2xy divided by x square plus y square. So it looks like this. See, at the origin, it's little weird. Let me see here. So from so see its behavior at the origin. Okay, so from different curve it goes to different points. Okay, so I'll stop here. In the next lecture we will see differentiability of functions of several variables.